telling us some evidence to show certain problems cannot be solved in polynomial time. And then in the last few lectures, we're looking at, okay, what do we do with such problems? So lots of different approaches. Okay. So start again. We are. The hope is to wrap up the course today. We looked at the big part of the course. We looked at a lot of polynomial time algorithms. This class P, which stands for all problems where you have algorithms which have an algorithm. Problems that have algorithms whose running time is some polynomial in the input size. So, n square, n cubed kind of algorithms we saw for flows, shortest paths, sorting, and a number of other problems. Then we looked at this notion of NP completeness. That was giving us some evidence to show certain problems cannot be solvable in polynomial time, and so the idea here is to not look at one problem, but somehow look at the relation between problems. We saw a number of problems NP complete. Now, the last 2-3 lectures, we are looking at how do we deal with problems that are NP complete, right? So, some of the approaches was look at some special instances where maybe you can design polynomial time algorithm. For example, a CNF SAT formula if every clause has at most 2 variables, vertex cover on trees, bipartite graphs, click on planar graphs, and so on. Okay, so that's one approach to deal with hard problems, is to see the boundary of the class of instances on which you can actually design some polynomial time algorithms. The other big approach is this approximation. We have looked at, so you look at an optimization problem and relax the condition that I really want optimum solution, and we are happy with something close to approximation. The big challenge is so we want polynomial time algorithm, but I am happy with getting something close to optimum, and the big challenge is to figure out how close to the optimum it is, right. That takes us to the notion of approximation ratio, and we saw a lot of problems, different kinds of approximation algorithms. We saw vertex cover has a 2 approximation algorithm, ratio 2 approximation algorithm, traveling salesperson problem. The most general version does not have any approximation algorithm at all, but if you assume the distances satisfy triangle inequality, then we saw 2 and 1.5 approximation algorithm. Set cover, the greedy approximation algorithm gives you a log n ratio, and there is nothing better known, or it's believed that nothing better is possible. Then we saw this subset sum problem, where we had a fully polynomial time approximation scheme, which means that basically I can get to any epsilon, 1 plus epsilon approximation ratio. So today I am going to look at another approach to deal with hard problems, and that is to deal with, I cannot approximate, somehow my problem requires me to give exact algorithm. There is nothing special about the problem, and it is an NP complete problem. So what that means is that I have to live with an exponential time algorithm, But in the exponential world, I am going to look at better exponential algorithms, right. So, we already saw some flavor of this. For example, dynamic programming. When we are looking at dynamic programming, we saw that for the traveling salesperson problem, the naive exponential time algorithm would be to try all possible permutations of your input and pick the one which has the total minimum distance. That's an n factorial running time, right, order n factorial times n, that can be improved to using dynamic programming. You will see more such examples. Largely this notion of branch and bound algorithm, right. And the sort of a sub area, if you like, is this area of parameterized complexity. Where we will analyze algorithms in a multi-dimensional way somehow, right. So, problems have, so your inputs have multiple parameters, right. Now, take any typical problem, there are many different, so far our approach has been to look at the input size as some important parameter, and our algorithm's running time was measured as a function of the input size, polynomial in the input size, exponential in the input size. But now this area of parameterized complexity says I have my inputs come with an associated parameter. We will see what kind of possible parameters are. And we will analyze the algorithm's running time both as a function of the input size and the parameter. Okay, and we'll say a problem. So, who gives you this parameter? We'll look at quickly see some examples, but this notion of feasibility here is fixed parameter tractability. Corresponds to having algorithms with time some function of k times polynomial in the input size. So, this exponent is a fixed constant, it does not depend on k. So, I am just splitting the algorithm's running time into sort of two parts, one that depends on the parameter and one that does not, that depends only on the input size. So, on the input size, which input can be very large, it is a pure polynomial, but on the parameter it is some function, typically exponential or worse. So, for what kind of problems do you have such an algorithm? So, P stands for polynomial time, right, an algorithm of this time. Now, we are extending this notion of feasibility to saying, not just polynomial in the input size, if there are some small parameters associated with the input, and if you allow your running time to be exponential or even worse, running time on the small parameter, the parameter is small, it is still a reasonable algorithm, reasonably practical algorithm. So, we will expand as a notion of feasibility to figure out for what problems will you have this kind of an algorithm. So, let us look at let us look at some example. So, I am going to spend some time talking about parameterized complexity first, and then we will get to exact optimization problems. Yeah.
She's saying she cannot hear anything, only video is clear. She's asking whether we can connect to Skype.
It's your call. If you can do that, fine. How do you?
I cannot connect the camera. This camera cannot be connected to Skype. Only the camera part of it has to go from this view and only the audio from the open mic I can just.
So they can't listen anything.
They cannot hear anything. But when we checked yesterday, audio from our side was very clear.
You decide. I'm ready. You tell me what I should do. I'll follow. You just see whatever works. Okay, so let's look at this example of vertex cover. So input a graph, undirected graph. I also have to give you a parameter because in parameterized problem you have to have some parameter, and the question is so my parameter for this example is the solution size. I am asking, is there a parameter, is there a vertex cover? I am not looking for an optimum vertex cover, I am not looking for minimum vertex cover, I am not looking for approximation. I am just saying I have a budget of maybe k is like 20, 30, some small number, I have this huge graph. Is there a vertex cover of size at most 20? Okay. So, what would be a brute force algorithm? Yep. Try all subsets of size at most 30 of this graph, and for each subset just see whether every edge is covered, right. If you delete it, you want to make sure there is no edge in the graph. How would you iterate? So, there is a okay, so there are some enumeration algorithms. There are some systematic way of enumerating all possible subsets of size at most k. Okay. You can think of enumerating all 0 1 strings with at most 130 ones, for example, right. So, a subset is a 0 1 string, right. A subset of a vertex set, is a 0 1 string. So, I systematically enumerate all possible subsets with at most 30 different ones, and give you all subsets of size at most 30. And pick up those vertices and see whether run through every edge and see one of the endpoints, is it in this vertex set, right. So, try all at most k. So we are going through an example for parameterized complexity, and the problem we want to look at is vertex cover. You are given a graph on n vertices and m edges. So in parameterized complexity, typically problems come with a parameter, and who gives this parameter? There are multiple different ways of parameterization. One way of parameterization, in this example, is the solution size. I will give you another example later. For now, the solution size is the parameter. So I am interested in asking, is there a vertex cover of size at most k, where k, imagine it is some small number, but k is k. So a naive algorithm would give you try all subsets of size at most k and check whether that subset covers all the edges, and the running time would be something like this. This is the number of subsets. So you have some careful enumeration of all subsets of size at most k, and you run through each subset and check whether every edge is covered. So it has a running time of this type. Okay. On the other hand, the running time is not of this type, because here the exponent on the input size is just independent of k. That's when I say the algorithm is fixed parameter tractable, if the problem is a fixed parameter tractable. So this is independent of k. So here I am okay with some exponential in k, and it turns out vertex cover has a very simple algorithm of this type. Okay, you don't have to do all this branching. And what is that algorithm? So what you can do is, so let me write here. So you this margin is good enough for me to describe the algorithm. So what is the algorithm? Don't remember. So what you do is you just look at any edge in the graph. You know that one of the endpoints must be in any solution, any vertex cover solution. Doesn't matter whatever size your optimum solution, k-sized solution, whatever, because this edge has to be covered. At least one of the endpoints must be in any solution, right? So I am going to do a branching algorithm, which I will try this edge, this vertex, or try this vertex. So I am looking for a vertex cover of size k. So here is my sort of recursive algorithm. While there exists an edge uv So this is a recursive algorithm. VCG of k will say yes if there is a vertex cover of size at most k, and say no otherwise. So what am I saying? Find an edge in the graph uv, check. I mean, one of them has to be in any solution. So I'm going to try. I pick u into my solution, delete it, and see whether in the remaining graph whether there is a vertex cover of size k minus 1. If there exists one of size k minus 1, I can pick that vertex cover and add u, and that together will be a vertex cover of size at most k. Otherwise, try deleting v and see. If neither of this succeeds, then you say there is no vertex cover, because I tried. I know both of this. So essentially, here, what are we trying here? We are exploring all possible solutions of size at most k. That's also same thing we are doing, but I am doing a little more systematically and using this extra information that I should. So this branch will explore all vertex covers containing u, and this branch will explore all vertex covers containing v. And anything that contains both u and v will also be explored in one of the branches. So if any of this succeeds, I'll say yes, otherwise I'm going to return no. Okay. Now how much time does the algorithm take? It's a recursive algorithm, so we will write a recurrence relation. But important thing is, I can even ignore the improved progress I'm making on G, but see what happens on K, right? I can even add another tail condition. If there exists an edge UV and okay, so if K is, so we always start with K greater than or equal to 0. If K is equal to 0, what can you say? The graph has an edge, but you are asked, is there a vertex cover of size 0?
No.
No. So the answer is no, because you know that there is an edge and I can't cover it. So if K is 0, return no. So else, so this is sort of a tail condition then. So K keeps, so what, if you look at what happens to K in these recursive branches, I start with G comma K here, then I do G minus U, K minus 1, and G minus V, K minus 1. And here I'll pick another edge and branch, it goes on. It's a two-way branch, right? What is the depth of this tree? K. Why? Because when K is 0, I'll get out. Right? K is 0, and if there is still some edge left, then the answer is no. And if I've covered already all edges, that means I would have even stopped somewhere in between, that even before K becoming 0, I would have exhausted all the edges. So that's a good case for me, right? That I don't even need my full budget, I've covered all the edges. So this depth is K. Branching factor is 2. So the number of leaves in this is a 2 power k, and in each node I am spending polynomial time. Okay, it's just about finding whether there is an edge in the graph, and then I am deleting a vertex and all that. So the number of recursive problems I have is 2 power k, and in each of these nodes of this recursion I am spending a polynomial time. So the overall running time of this algorithm is 2 power k times some n square or something. If you carefully analyze, you can do even as good as n square. Okay. But for me to say it is fixed parameter tractable, I'm happy with any polynomial running time here. It's an f of k times polynomial in the input size. On the input size, so n can be very large. I'm just doing very good, n square or n log n or n cubed kind of an algorithm. On k, I'm doing some exponential in k. It is an NP hard problem. I have to live with exponential dependence on something. So, and this is clearly a better algorithm than n power k times m, because when k is like small 30, you have an n power 30 algorithm, whereas this is like a 2 power 30 times n square. Okay, so such algorithms are good, and such problems are called fixed parameter tractable, that I can separate the dependence of the parameter and the dependence on the input size. On the input, it's just polynomial, and I can have this refined running time. Okay, now it's not that, not just that. You can do even much better. I'll give you quickly we'll improve this algorithm. So here the observation was that if you have an edge, one of the endpoints must be there. So all we are saying is, when you are trying all possible subsets, don't just explore a subset which avoids an edge completely. That's all we are saying. If you want to make sure that every edge is touched, then you don't need to try n power k. You just need to do 2 power k kind of solutions, right? I have a graph like this. I am looking for a vertex cover of size 2, let's say, then there is no point in trying this subset of size 2 because it completely avoids this edge. Because I know that that's not going to be vertex cover. That's all we are using. You just say that for every edge, one endpoint must be there. Now let me use another simple observation. We'll get some better algorithm. Okay, another observation. Suppose you have a vertex x, and here are its neighbors. If x is not in the solution, then what can you say?
If neighbor of x doesn't have any other neighbors, then these vertices should be there.
So I am trying to cover all edges. Suppose x is not in the vertex cover I am trying to pick,
10x
then
should be there. 10x should be there.
at least one of them, all of them should be there. Entire n of x should be there, because if x is not picked in the solution, who is going to cover this edge? This vertex. Who is going to cover this edge? This vertex. Then n of x is in the solution. Okay. So now I'm going to, this suggests another branching algorithm. Let's write another branching algorithm. So let's first of all remove isolated vertices. They play no role in covering edges. Right? Now pick any vertex x. My two branching is include x into the solution, and another one says exclude x in the solution, then include all its neighbors. So return S if vertex cover of G minus x. What is the recursive budget I am allowed? If I pick x into the solution, then in the new graph I am looking for a vertex cover of size k minus 1. If I don't pick, then k minus the size of n, degree of x. That's it. So pick x into my solution, in the delete it, in the remaining graph look for a vertex cover of size k minus 1. If I find that, add that to x and I got a vertex cover of size k in the graph. Otherwise, delete x, delete its neighbors completely. So that means all its neighbors are all gone. Now the n of x is included into my solution because x is not there. So in that other branch, I am looking for a vertex cover of size k minus the degree of x. Because I have picked so much into my solution.
Okay, yeah, that's the size.
That's neighborhood of x is same as the degree of x, right? Two-way branch.
I could carefully choose the vertices according to the degree. Then
Exactly. We'll come to that and see how much I can improve it. But let's see what is the running time of this algorithm. So again, focus on k. What happens, right? Like we did here. So two-way branch. So if you know everything else is a polynomial time on the input side. So if I write it as t of k. Here it was 2 times k, t of k minus 1, so that gave us 2 power k times some polynomial input. So here it is, in this branch it's t of k minus 1, in this branch it's t of k minus degree of x can be as bad as 1, so also gives you k minus 1. Right? If x happens to be of degree 1, then I delete x. In this branch, I pick its neighbor, which is sort of like the same kind of a branching, if it's degree 1. But this gives you a 2 power k times whatever, some polynomial running time here. Okay, but now as Abdul says, why not pick a vertex with high degree, right? Then my branching would be skewed. In one branch it will be 1, in the other branch I am going to pick a lot of vertices, right? So pick a vertex x with degree greater than or equal to 2. Let's see what happens. If I pick a vertex whose degree is greater than or equal to 2, then in one branch I pick x, so k drops by 1. In another branch I pick both its neighbors, so k drops by 2. So what is the recurrence? At least k minus 1 plus k minus 2. So what is this? It's a Fibonacci recurrence. So you get 1.618 power k, right, base. But of course you should ask the question, what if there is no vertex with degree is greater than or equal to 2? There has to be.
All, how can all be pending?
Then it's a cycle.
But there will be something greater than
There is nothing with degree greater than or equal to 2.
No, if vertex size is more than 2, then how can?
then it will be a
It's,
match.
so what if the whole graph is a matching or something?
Yeah, pick just half of the n by 2. Like
Oh,
then we just have to check whether n is less than k.
So there could be, okay, we have removed isolated vertices. So if every vertex is degree exactly 1, right, because we have deleted 0, and if it's greater than or equal to 2, we are doing progress. So when do we stop? When every vertex is degree exactly equal to 1. So that means the whole graph is a matching. So you need exactly half the vertices. Whatever it is, you can solve it in polynomial time, right? When we reach that stage, you can solve your vertex cover in polynomial time, right? We can even do better. So why don't I pick a vertex whose degree is greater than or equal to 3? Let's see how far we will go. Then what happens to the branching here?
K minus 1.
K minus 1, and this is k minus 3. I think this is some 1.5 or so. Forget what the solution is. Okay, how do you solve these kind of recurrences? Hopefully you have seen it in your discrete math course or something. Use some generating function or write some characteristic equation for this and then solve it. Okay, but then again, what if there is no vertex whose degree is greater than or equal to 3? As long as you have a vertex whose degree is greater than or equal to 3, you will keep branching like this. Then you reach a leaf where there is no vertex whose degree is greater than or equal to 3. That means every vertex has degree less than or equal to 2. So 1 or 2. How does the graph look like? It will just be paths and cycles. You can solve it in polynomial time. If your graph is paths and cycles, you can solve that in polynomial time. Right? Can I do this again and see? If I do this 4, I am going to do much better here. But what is the tail condition? I am left with a graph where every vertex is degree at most 3. Unfortunately, vertex cover is NP complete even on such graphs. Okay, so at least this approach doesn't get you anything beyond that, because if vertex cover is NP complete on cubic graphs, graphs whose degree is less than or equal to 3, even in that class of graphs, it's NP complete. If your degree is less than or equal to 2, then it's paths and cycles, you can solve in polynomial time. Okay, so but you see that we started off with such a hopeless algorithm. Now we could improve it to not just 2 power k, we can just quickly, with some very simple ideas, we can get as well as 1.5 power k out.
The way you constructed the tree, so if we choose the vertices according to the decreasing degree, then the tree size will be minimum. So it will give the best result when the vertices will be chosen.
Yeah, but what if the graph is a regular graph? Maybe all vertices have the same degree or something.
In worst case, it's okay, but in general.
Yeah, so generally you pick a vertex with very high degree, sure. pick the highest degree vertex and branch. That's always a good heuristic because the drop is pretty high, right? Because you get a very good drop here. True. So now, so this is a very nice example problem for parameterized complexity. We just, with very simple observations which got you very far. Now, I mean, this is like, we are still talking about a 2-line algorithm. Now, there are algorithms that run for 2-3 pages, and the current best algorithm looks like this, which has something like this. In fact, you can even write this is the current best. So it's fixed parameter tractable. One of the few problems where you have such an efficient running time, but you get the idea of what we are looking at. We are trying to separate for certain, when certain parameters are small, you just want to avoid brute force running through all n choose k and get an algorithm. So regardless of n, this is a fairly efficient algorithm for moderate values of k. You can go up to k is 50, 100, it's pretty reasonably manageable running time. So solution size was the parameter I used. I'll give you another example. Let's still work with the vertex cover. But let me change the problem now. I want to find the minimum vertex cover. So I am solving the optimization problem. But then what is the parameter? So we know how to solve vertex cover in linear time on trees. The input is a tree, some simple dynamic programming, or you just say, as long as the vertex is degree 1, I pick its neighbor. Don't pick that vertex and pick its neighbor and keep doing it. This actually solves the whole problem for vertex cover on trees. Okay. So now suppose the graph is such that it's tree plus k vertices. So that means it's very close to a tree. Graph GB such that there exists a set S G minus S is a tree. And the size of that set is my parameter. So that means all I'm saying is my graph is k away from a tree. Okay, it's close to a tree. In tree I can solve it in polynomial time, I know, linear time. But suppose the graph is simply k away from a tree in the sense that there are some k vertices, if you delete it and it becomes a tree. Okay. And you are also given this S, let's say. If S is not given, there are ways around it. Suppose, so a graph G and you are given all this. And I want to find the minimum vertex cover. So imagine your structure is, here is my set S and here is the rest of the graph. So this is a tree. But in S it could be anything and there are lots of edges like this. And this is small. Now I want to find a minimum vertex cover. It turns out my parameter is not the solution size now. The parameter is some structure of the input. The input is very reasonably close to a tree in this sense that there are some k vertices. If you delete, the graph becomes a tree. Okay. Now I want to find the minimum vertex cover. And you are allowed time f of k times some polynomial in the input. And we know that on a tree I can find the minimum vertex cover in linear time, polynomial time. Okay? So, how do I? So, you can be exponential in this size, right? So, you should take advantage of that. That I am happy to be taking time which is exponential in this part of the input, the rest of it should be linear. No ideas.
You look at all choices of S.
All choices of
S will be size k, so n choose k.
n choose k
N is the number of vertices
in the whole graph.
in the whole graph. And so I'm saying that if I pick k vertices from that, it's a possibility that it is this S.
But I don't want n choose k. Remember,
No. Oh yeah, I know that.
I am looking for. This is not a good,
Yeah.
not allowed running time. I am willing to spend. Yeah.
Huh.
So if I take minimum vertex cover in V minus S
Hmm.
and add those vertices in S that are not covered by those vertices, will it
Look at
be
all
a-
subsets of this.
Okay, so what you are saying is find a minimum vertex cover in V minus S, which I can do it in linear time. That covers already, it covers all edges here. It may be covering some of these edges, and whatever it is not covering,
that
just go and pick that. It sounds like a greedy thing, right? You may, first of all, that's a polynomial time algorithm. It's not even f of k. Okay, and secondly, it is greedy because you are focusing on covering all edges here, and so you're in that process. You may, it may not pick. So if let's say it's a star or something, then the optimum vertex cover will be middle vertex. Suppose this tree is a star. If you focus only on this, then the optimum would be just the middle vertex, which will force you to pick pretty much all the vertices here. But if you just take a global look at it, you may be able to do something else. Okay, so your idea is sort of do a reverse of what you said.
So look at all subsets of S.
Look at all subsets of S, right? So I am looking for a minimum vertex cover. That minimum vertex cover will intersect S somewhere. Let's say S prime. That S prime could even be empty for all you care. But the minimum vertex cover, okay, let S prime could be S intersection opt vertex cover. I don't know this because I don't know opt vertex cover, so I don't know S prime, but I can try all possible S primes because I am allowed 2 power k running time. So try all possible. So I guess the intersection of S with my optimum. Let's say it intersects at S prime, right? Then, so what am I saying? From S, in the solution I am looking for, I am going to only pick S prime. So the remaining guys I am not going to pick.
but can verify that is it a vertex cover?
Yeah, so there may be some edges here. That means I have to abandon that guess and move on to the next case, right? Because if I say that my intersection with optimum is only this, then the remaining better be independent. Because otherwise I just move on to the next case. Then after that I am done. Once I guess my intersection, then I know that the rest is independent. Since I am not picking this, I am forced to pick their neighbors. I pick that into my solution. I pick this into the solution. Now delete them. What am I left with? A tree where I can find the optimum vertex cover in polynomial time. This is the idea. I am going to try all possible guesses.
That's what I was thinking, to take arbitrary subset of S, we can verify it whether it is a vertex
Sure.
cover in
Of
polynomial
S or
time,
not.
and check the subtree in polynomial time
Yep.
in V minus S.
Right.
That will also.
That's all. But that still may not be the optimum vertex cover, because your S prime may not be a good vertex cover. So you're going to try all possible choices of S prime. Yeah. So let S prime. So try all subsets S prime of S into the solution. Pick neighbors of S minus S prime, right? S minus S prime, these guys neighbors, they will only be here, pick them, and then solve vertex cover on the remaining tree.
So why on the remaining tree we can also exclude neighbor of the neighbor of S minus S dash?
Sure, exactly. Yep. Yeah. So you're going to pick this into your solution, pick this into your solution, delete them. Delete these vertices. Now what you have is there a tree there. You solve it in polynomial. And you get some size. Try all possible subsets of S prime and why? I mean, so this gives you a 2 power k times whatever time you need to solve tree. I mean, why can't, I mean, why do we even expect there should be exponential dependence? Because when you told an algorithm, I said, oh, you have a polynomial time algorithm. That sounds impossible. Why not? Why can't I solve this whole problem in polynomial in n and k?
So every graph you can have some tree. You can divide. Okay.
Suppose I have an algorithm which is polynomial in the whole input size and k. Look, can I not write any graph like this for some s? Right? I mean, in the worst case, s could be n minus 2 or something of size. So just delete everything except an edge. Right? So there is an s contained in V such that G minus S is a tree. Just keep only one edge and delete everything else. Clearly there is, S is actually feedback vertex set, if you remember. It kills all the cycles. So any graph can be written like S and G minus S, where this portion is a tree. I mean, it could be an edge or something. So if I have a polynomial time, then I can actually solve minimum vertex cover in polynomial in input size. I don't expect. So this is, okay. So that's just a snapshot of what parameterized complexity is about. So the parameter can be anything which makes sense. So in one example, we saw the solution size as the parameter, and you saw a very good, efficient, fixed parameter tractable algorithm. In the other example, where the parameter is how far away it is from a tree. Actually, instead of a tree, I can even use a forest. It's no problem because I can solve in forest a polynomial time. So that means this is a feedback vertex set, really. So if you have a small feedback vertex set in the graph, then in f of the size of the feedback vertex set, so I'm going to spend some 2 power k time, then I can solve. So this sort of extends this notion of, I mean, we know there are problems which are solvable in polynomial time. There are problems, there are instances on which a problem is solvable in polynomial time. There are instances on which it's NP hard. This gives a smooth thing between them, right? So you make it exponential, and if k is like log n, then you have a polynomial time algorithm. Okay, so that's this notion of parameterized complexity. I mean, we'll do a whole course probably next semester on this topic. So let me just move on to the starting thing which I said about exact exponential algorithm. Right? I'm going to give a couple of examples. So this branching idea is very powerful. Right? You're trying all possibilities, but in a very careful, systematic way that You can control the number of solutions you're trying. So let's look at again while we are at vertex cover. Let's finish. Suppose I want to find the minimum vertex cover in a general graph. Right? Find. This is the optimization problem. No structure, nothing. A brute force algorithm would be try all subsets of the input and see whether pick the one which is a minimum vertex cover, and whose running time would be 2 power n, right? 2 power n into m or something. Now, what is the goal in this exact exponential time algorithm? Again, is to improve the base. Right? We know we have to live with exponential time because no structure. I am looking at exact algorithm. Now, can I improve the base? We have learnt already enough to improve the base of the exponent.
For k, search for k.
Search for k. Why 2 power k? I told you much better algorithm.
Yeah, 1 point something.
Yeah, 2 power k doesn't give you what I'm aiming for. But if you use, so what we saw was that is there a vertex cover of size k? You can do it with, okay, clearly I gave you this Fibonacci recurrence, right? To test and actually I gave you even better than that, but let's say 1.6 power. Can I not use this to get the minimum vertex cover? So what do? So if you tell me a k in 1.6 power k times some polynomial in n, I can tell you whether G has a vertex cover of size at most k. But I actually want the minimum vertex cover. So how can I use this?
Do a binary search on the.
Yeah, you can do binary search. You can even do linear search. Even use linear search, right?
Find k.
Try all values of k. Try k equal to 1. Is there a vertex cover of size 1? Run this algorithm. Is there a vertex cover of size 2?
We'd have to try from n by 2 and
Or go from 1 to n by 2, whatever. Even if you go up to n, how much time does this algorithm take? Right? Go up to n minus 1. So what is the running time? It will be summation 1.6 power I, even if you go all the way up to n. It's a geometric series, right? Well, I'm ignoring the n to the c term. What is this? Yeah, plus 1, right? Whatever, if you ignore all of that, this is basically 1.6 power n. Everything else is a big O, right? You look puzzled. It's a completely trivial thing. If I can test for a particular k in this much time, try all possible values of k. It's a geometric series. When you add them all, you're beating 2 power n, right? So this is not only useful for testing whether it's at most k, you can actually improve the base for the optimum solution also. But sometimes actually optimum can be done better, because if you do the branching, no. So let's say I pick a degree, what did we say, degree 3 vertex, and I said degree 2 or less in polynomial time you can solve it. I pick a degree 3 vertex and I branch, right, x in solution, neighborhood of x in solution. So k, the solution size was dropping by 1 here, dropping by 3 here. So the branch factor was 1, 3. But if I look at n, the number of vertices, what is the drop here? N drops by 1 here and n drops by 4 here because x is also gone. So the branch will be better. So sometimes the same branching algorithm, if you use the solution, the input size as a parameter, then you actually get a better branching. So anyway, so these kind of algorithms are immediately useful to give you a better than 2 improvement on the base of the exponent. We'll see a couple of more examples of just, so the idea, the goal here is this. I am looking at a hard problem. I have to live with exponential runtime. No structure, no approximation. I am looking at exact exponential algorithm, improve the base. Right? Parameterized complexity brings in this parameter and says separate the running time dependence on the input and the parameter. Here I am, there is no parameter, but improve the base. So let's look at 3SAT. Okay. Given I want to know whether is it satisfied. We will see some simple algorithms. So what would be the brute force algorithm here? Try all assignments to your n variables, 2 power n, and for each assignment, run through your formula and check whether it is satisfied, right? So the naive algorithm would be 2 power n into m. Okay. But like vertex cover, we know that there are certain assignments you should not even try. So let's make use of that, right? We said in the vertex cover, instead of trying all possible subsets of size k, we said, any subset which avoids an edge completely, don't even bother trying it. So like that, suppose in my formula, I had, let's say x1 or x7 bar or x3 is one such clause. Okay. Clearly, some assignment I shouldn't even try testing whether it is satisfied. Which assignment?
0, 1, 0.
So if I set x1 equal to 0, x7 equal to 1, don't even bother trying any assignment which does this for these 3 variables, right? So how many assignments do you save in the process? So I'm saying try all assignments to the n variables except these 2 power n minus 3, exactly, right? Because it just says out of the 2 power n, of the remaining you try all possible assignments, for this don't do this, right? So you save this much. So the number of assignments you will do is 7 by 8 times, okay? So that's not an asymptotic improvement, but it's slight improvement. But it turns out you can use it recursively and get a better algorithm. So what is a recursive algorithm? The recursive algorithm, let's say this is one clause, okay? Then I will have a branching for these 3 variables, just for these 3 variables. Okay, so is the whole thing clear? So what he said is that if I just want to avoid assignments that sets for these 3 variables, these values, then I just have to try 7 over 8 times 2 power n. That's still a lot. Asymptotically, I didn't make any savings. It's still 2 power n. Right? You just save on 2 power n minus 3, which is 1 by 2 power n by 8 assignments you save, but the remaining you have to try. So instead I am just saying I give you a branching algorithm like the vertex cover branching. So recursively check f with x1 equal to 1, x7 equal to 0, x3 equal to 1, or f with, basically there are these 7 assignments you want to try, right? For these 3 variables, there are 7 possible assignments. So I am going to do a 7-way branch. I just take these 3 variables, I pick one clause which has 3 variables. On these 3 variables, instead of trying all possible 8, I am going to try 7 possible assignments. Simplify the formula, which means that these 3 variables will go away from the entire formula. On the new formula, recurse and see whether it is satisfied. Whether any of this what would be the running time?
To the power
7 to the power m, okay. So what is the depth of this recursion? Okay, everything boils down to answering that question. What is the depth of the recursion? So what do I do in one branch? So
For each class I am taking that
Hmm?
For each class I am taking that
not each class. Think of it as I'm just picking some 3 variables, setting them. That is the progress I am making.
Why anything not only
Low and best three.
Close.
and why is there anything not only in the clauses?
I mean, this clause guides me to avoid one assignment. That's all. Really, what I'm saying is I'm going to pick these 3 variables, x1, x3, x7. I could have just done any variable. That's what gave us a 2 power n algorithm. Just for each variable, we pick 2 branches. Instead, I'm going to use a clause, and in this, now on these 3 variables, normally I would have tried 8. Now I'm going to try 7. That's what this clause tells me. So I have a 7-way branch, and I have set 3 variables.
Low and best three.
Why log? Why log?
There initially it were n. Oh, n by
7 power n by 3, right? So this is 7-way branch,
yes.
and 3 variables are set. Okay. Now I go to a, so in this formula I'm going to pick another clause. Actually some clause may actually have only 2 variables after this assignment. Okay, that complicates analysis a little bit. Maybe it works in our favor. Then it will be, then I will try 3 out of the 4 assignments for those 2 variables. So in the worst case, I keep picking 3 variables. I'm trying 7 possible choices, right? So 7-way branch, and the depth would be n by 3. Each time picking 3 variables, 3 variables, 3 variables. So it's 7 power n by 3. Which is 7 power 1 by 3 whole power n. It's better than 2 power n. It's 1 point something power n. Right? It is like, remember, I mean, this idea strikes back again. Strassen's matrix multiplication algorithm, right? We did 2 by 3, 2 by 2 matrices. Instead of normally doing 8 multiplications, Strassen came up with a way to do 7 multiplication. But that alone, when you apply it recursively, it gives you an improvement on the overall running time, n power log 7. Similarly here, just moving from here, we could just doing it recursively, we get something better than 2 power n. Okay. Now, remember I said in some assignment, actually when you go, you might actually have a formula which has only 2 variables, because by setting maybe x1 equal to true, there was another clause which said x1 bar or x5 or x6. This has gone away. So there are only 2 variables. Then in that 2 variables, instead of 4, you are going to try 3 possible choices. That actually works in your favor when you do the analysis. Now, if you do this combinations and do carefully pick clauses to branch, you can even do much better than 7 power 1 by 3. I think again this has gone through a lot of development. The current best for 3 SAT is something like this. So improve the base, that's the goal, right? But interestingly, if I remove this 3 CNF formula and say it's an arbitrary CNF formula, there's no bound on the length of the clauses, then we know nothing better than 2 power n. We don't even know 1.9999 power n algorithm. Okay, so what is this saying is that all NP complete problems are not the same in some sense, right? Vertex cover you can get some 1.5 power n, 3 CNF you can get 1.58 power n, but general CNF formula we don't know anything better than 2 power n. Okay, so in the exponential world also there are all kinds of different problems, and it's conjectured. This is a conjecture which says exponential. Okay, there are 2 conjectures, exponential time. So even 3 SAT, can I keep doing this? I mean, how far can I go? Can I get 2 power square root of n? Right? Exponential time hypothesis says that no 2 power little o of n algorithm for 3 SAT. This is just a conjecture, we don't know. And strong exponential time hypothesis says no 2 minus epsilon whole power n algorithm for SAT. This is also a conjecture. So for general SAT, we know nothing better than 2 power n. For 3 SAT, we have very good algorithm with much less than 2 in the base. But we don't know 2 to the power little o of n. We don't know it. So this tells you that even improving 2 power n is sometimes not very obvious. So I'll end with a good exponential time algorithm for a dominating set. Okay, it also uses branching and so remember what is a dominating set? I don't know where it is. If for every V not in S, there exists a U in S such that UV is an E. So it's different from vertex cover in the sense that for example, S is dominating here in this graph because if you pick any vertex outside, there is some neighbor inside. That's a dominating set. It's not a vertex cover because these edges are not covered by S. So it's vertices covering vertices, whereas vertex cover, vertices covering edges. Okay. Alternatively, the neighborhood of S is the entire vertex. If you pick this vertices and go look at all its neighbors, you will include all vertices. And one is always interested in a minimum dominating set, right? So what's a brute force algorithm? Try all subsets. You're looking for a subset. So try all subsets and just go through every vertex and see whether anything which is not there, there must be some neighbor here. So it's again a I'll give you an, so some of these problems, can you get something better than 2 power n was an interesting open problem for some time. I'll just give you a simple nice branching algorithm. Unlike vertex cover, branching algorithms for dominating set are not very easy, because once I decide I am going to include a vertex into my solution, in vertex cover I can delete it and work on the remaining graph, but here I cannot. Do you see the difference? Suppose I say, here is my graph and here is a vertex, I am going to branch. Suppose I include it in the solution. Okay. Can I just delete it and work on the remaining graph and find a dominating set? What's the problem?
There are some.
So there are neighbors of these vertices which are dominated by this vertex. So there are like 2 classes of vertices here, some which are dominated already, but can I delete these vertices maybe?
That would be dominating some of
They could be useful to dominate others, so I can't. So the problem is not, after you delete a vertex, the problem is not the same as what it was before, because there are 2 kinds of vertices, so branching algorithms get a little messy. So what we'll do is, I will convert it to a set cover problem. One can easily visualize this as a set cover problem. I'll give you a good branching algorithm for set cover. Okay. So how do I convert? Do you see that it's actually a set cover? Let's give a reduction to set cover. Remember, set cover is a universe and the family of sets. So what is the universe? Vertices, because that's what you want to cover. So my universe is vertex set, and what is my family?
Neighborhood.
For each vertex I pick its neighbor, right? Close neighborhood. So there is a set for each vertex which will contain all its neighbors. So that means if I pick that vertex, it dominates itself and all its neighbors. So the smallest subset of vertices I am going to pick will be a smallest subfamily that will cover the universe. Okay. So now I am going to, so what is the size of the universe and how many sets are here? N, right? Both are N. So if my graph means my U is N, the size of the family is N. Okay. So now I am going to give you a branching algorithm for set cover where my measure, what drops, would be also the set and the universe. Okay. So it's a very simple branching algorithm. Branching algorithm for set cover. So before that, let's do some simple pre-processing. Like for vertex cover, we said delete isolated vertices kind of things, right? So suppose some vertex appears in only one set, some element appears in only one set. What can you do? Right? If some x is in U appears in only one set, that set has to be chosen in my solution because that's the only set covering that element. So include F in the solution and delete from the universe. So U, I will update it to be U minus F, because anything F is covering, I can delete it from my universe. I can also delete all these elements from sets in the family also. They've all been covered, right? I can do more things. Okay. If F1 is contained in F2, what can I do? Remove F1 because I am going to pick small number of sets that together cover my universe. F1, F2 will cover F1 elements also, so remove it. Good. Now, at the end of this, every set F in F has size greater than or equal to 2. Do you agree? Because suppose you have a singleton, either it appears only in that set, I would have deleted it, or it also appears somewhere else, but then this is a subset of that. We'll also assume that no two sets are the same, right? Actually, yeah, even if F1 is equal to F2, I would have deleted it. Okay, good. So now my branching algorithm is okay. Pick set F such that first let's say cardinality of F is greater than or equal to 3. If there is such a set in one branch. So now I can tell you how the branching algorithm works, right? We have seen pick F in another, don't pick F. Okay, that's my two branch. I just arbitrarily pick a set. Only thing I need is it has at least 3 elements. We'll deal with what if no such set. I just pick F into my solution or do not pick F into the solution. Okay. When I pick F, so my measure is going to be the size of the universe plus the size of the family. Okay. What is this measure? We'll come to that. So tell me what happens to this measure in each of the branches. In this branch, what happens to mu? So I pick F into my solution. So what happens? F is out of my family. All elements covered by F is also out of my universe, right? So F is size at least 3. So how much does it drop by?
By 3. By 4.
By 4, right?
By 4.
The universe drops by 3, family drops by 1. So mu would be at least or at most mu minus 4. Okay, what happens here? I don't pick F. I just don't drop F from the family. That's all. I don't do anything else. Drop F from. So it drops by 1. So what I have is a 1-4 branch. Right? Remember 1-1 branch was like a 2 power k, 1-2 was Fibonacci, 1-3 was 1.5 and 1-4 happens to be 1.4 1.4 power what? My measure, right? Because that my recurrence is on the measure. So 1.4 power mu. What is mu for me? For my dominating set example? 2n. So this is less than square root of 2, less than 2 power n. Okay. My aim was to get a 1-4 branch because that way my base would be less than square root of 2. My mu is 2n. So this whole thing would be some 2 minus epsilon. Because I am just trying to get an algorithm whose running time is better than 2 power n. Okay, the only thing which I assumed is that the size of F is at least 3. Suppose there is no such F, then every set has size exactly 2, right? Now you can solve set cover in polynomial time in such an instance. Otherwise, let's do some branching and get something better. My aim is to get this kind of a branching, right? Okay. 2 minutes, it should be done. So if I have every set has size 2, then let's see how, if suppose I do the same kind of branching. So if f is greater than or equal to 3, I used it and I get a 1,4 branch. So my solve recurrence, write down a recurrence in terms of mu. So t of mu would be less than or equal to t of mu minus 1 plus t of mu minus 4, and this gets me strictly less than square root 2, square root of 2 minus epsilon power mu, and mu for me is 2, so the whole thing is less than 2 power n. The only thing is, if every set has size exactly 2, I don't get this guarantee. What do I do? So suppose I branch, right? I pick this set F and I branch. So include in solution and exclude. When I exclude, the measure again drops by 1 because this set goes away, that's all. But when I include it, let's see what happens, right? This universe drops by at least 2 because 2 elements are out. F drops by 1, so I get only a drop of 3. I want to get a 4. But then I use the fact that, remember, these 2 elements are also appearing somewhere else, right? Because we said every element appears at least twice. So this element may appear somewhere here. So once I pick this into the solution, this set covers that element, so that element I can remove it. That means the other element becomes a singleton, and we have a way of getting rid of the singleton, so this set will also go away. And similarly, the other element, so at least one more set will go away and I get a branching factor of 4, 1/4. Okay, so what is the moral of the story? I mean, I wanted to give a 2 minus epsilon. So first thing is, can you get something better than 2 power n for every problem? We don't know. Problems behave differently, and it's an interesting open problem sometimes. For a dominating set, one way to do it is first convert it to a set cover instance, and then we give a branching algorithm for set cover based on these simple rules, and then we branch. Branching algorithms are, usually not very hard. The clever thing is to make sure you get good drops in whatever measure you are thinking of. Okay? And we can get something better than square root of 2 on the base, but the power is 2n. Overall, it gives you something better than 2 power n. Okay, so that gives you some interesting flavor of some of the techniques and interesting problems in the exponential time world as well. Okay, so that's a whole interesting area. And there is a recent book by Ferrer Fomin and Dieter Kratz, Exact Exponential Algorithms. Lots of algorithmic techniques, branching, dynamic programming, inclusion, exclusion, some algebraic techniques. Many of this are used here. Yeah, okay.